Method of Legrange multipliers for functions of two variables. So we're going to wrap up Lagrange. We're going to look at functions that are initially of a single variable. We're actually going to look at calculus 1 problems that you did back in Calc 1, but you didn't use the method of Lagrange. You used the method of having to reduce the function of two variables to a function of one variable and then doing all the calculus 1 stuff on it. Find the derivative, set the derivative equal to 0 to get your critical number, and then do another test to determine if you've got extrema or not. So please do not teach your calculus 1 friends how to do this technique, okay? Even though you are learning it today when you're tutoring them, because they may not be even allowed to use it and their calculus 1 instructor will mark them wrong. Okay, so here's what we're doing. You're going to be trying to maximize a function of two variables or minimize, and you're going to have a constraint because in order to use Lagrange, you can't use it without a constraint. Then the max or min is going to occur at one of the critical numbers of your new function. And this is the Lagrangian I always talk about. The new function is going to be big L, only this time you're going to have a function of three variables, x, y, and a Lagrange multiplier, lambda. And the way you set it up is just like we did before, the function that you're trying to find the max or the min for, minus lambda multiplied by your constraint function. And you're going to optimize that. You're going to find the critical numbers for that and then get the problem solved. So the last couple of problems I'm doing here are classic, okay? So we're going to do another distance kind of problem here, okay? So this is classic because we did a distance problem last time, but it was in 3D. And now we're just doing another distance problem, but we're in 2D. So I can draw this like everybody is familiar with the parabola, you know, y equals x squared. That's an easy one to graph. Okay, fine. So here's the parabola. Okay, and that's your constraint. You're not going to do calculus on that parabola guy, okay? That's your constraint. They're giving you the point 0.03. So here's the point 0.03 right there. And they want to know what the minimum distance is from that point to the parabola. They want to minimize the distance. Well, if we want to eyeball this and look to see what would be the minimum distance from that point to the parabola, I claim because of symmetry, there's actually going to be two answers. Yeah, one to the right and one to the left. This one and this one. And these distances D are really the same distance. My drawing isn't that great. But the question is, what are the coordinates of these 2 points on the parabola that minimize the distance between that point P and the parabola? So what we're going to do is we're going to give one of the points, we'll just give it unknown. We'll call it X, Y. And those coordinates, X and Y, are the unknowns. Go get them. Get it done. Well, can I guess? No, you can't guess. This is a guessing game. Do this analytically. So, well, the distance between 2 points you learned in an algebra class long ago. So you're just going to use, you know, the square root of the sum of the squares of the differences between the y coordinates and the difference between the x coordinates, you know, like so. And so we want to minimize this. Now, just like we did last time, it's no fun to take partials of functions that have square roots in them. So the claim is minimizing the distance D. So here's our claim, and we're going to stick to it. We did this already before. Minimizing the distance D is the same as minimizing the radicand. In other words, if we minimize the radicand, the stuff that's underneath the radical, that will equivalently reduce the value of the distance. So what we're going to do is we're going to just look at what's under the radical and minimize that. So we'll call it fxy. And fxy is this. So let's try to minimize that guy. Subject to the constraint that y equals x squared. We're going to rewrite the constraint because you have to. You have to get your constraint written as everything on one side and 0 on the other. Uh-oh, there's that again. And it doesn't matter which side of the equation is got the stuff and which side has the 0. I don't care. And there it is. So you got your constraint rewritten. And now you're ready to write your Lagrangian. So the Lagrangian, as Professor Vallone would say, the big mother of a function here, L, X, Y, lambda, is going to be the function we're doing calculus on and minimizing the distance minus lambda times your constraint. So it looks like that. X squared plus the quantity y minus 3 squared minus lambda times the quantity y minus x squared. Go do stuff on that. So you're going to get 3 partials because this is a function of 3 variables only. Okay, so the partial with respect to x is 2x minus lambda times whatever inside of parentheses, but the derivative of that with respect to x. And I think that's negative 2x, but then a negative times a negative is a positive, and then I'm going to set this equal to 0. Now go get the partial with respect to y. I'm going to use the chain rule, 2 times y minus 3 to the 1 power times the derivative of y with respect to y, that's just 1, minus lambda times the derivative of what's inside parentheses with respect to y, but that's just 1, set that equal to 0. And then, of course, when you take the partial of your Lagrangian with respect to lambda, it's always going to be minus your constraint, and after you set it equal to 0, it's the same as your constraint equation. And don't go, oh, well, that's just useless. No, that's part of the deal. In fact, after I do some algebra, I always come back to my constraint. That's where I plug stuff in. That's part of the system of equations here. Very nonlinear system, that's for sure. So now, if I use that technique that I went over last time, which works most of the time, although it's not going to in my very last example. I'm going to show you that as my grand finale there. So for this equation here, let's solve it for lambda. So if I subtract x or 2x from both sides, I get 2 lambda x equals negative 2x. And then assuming x is not 0, so I can do this, if I divide both sides by 2x and then reduce to lowest terms, lambda, is a constant. Oh my God. What do we do? Don't worry. This is a little bit different flavor from everything I've done before. That's why I threw it in my lecture notes. I really want to be thorough here because sometimes nonlinear systems can throw you a loop. They're not always, oh, just do it this way every time. So what about the other partial? Go solve that guy for lambda. Well, that's easy because I'll just add lambda to both sides and I'll get lambda is 2 times the quantity y minus 3. Okay, now what has to be true? Well, lambda has to be equal to lambda. Okay, so that always has to be true. So we're gonna, you got to have that still be true. Can't all of a sudden, you know, go, oh, well, it's not true now. Oh, no, it is true. Okay. So you're going to go, all right, lambda has to equal lambda. So that means that negative 1 has to equal 2 times the quantity y minus 3. And then solve this for y. Okay. I'm going to first divide both sides by 2. So I have negative 1/2 is equal to y minus 3. And then how about if I add 3 to both sides of the equation? And I get y is equal to negative 1/2 plus 3. What the heck is that? I get 5/2. Now, how do you get the x coordinate? You got a y coordinate because you were solving the system. You know, this is what we have so far. Y is 5/2. What's the x? Well, use your constraint. The constraint is the parabola. You know, this whole problem, if you look at the picture again, let me remind us that we're trying to find the coordinates of this mystery point. Okay, but that mystery point has to live on the parabola, otherwise it's not going to satisfy the criteria. So if we substitute into our constraint when y is 5/2, we get x squared has to be equal to 5/2. Well, I'm going to square root both sides, but what do I have to remember when I square root both sides?
Plus or minus.
So x can be plus or minus the square root of 5 halves. Oh my gosh. So what does that mean? We have two critical points, and they're both equivalent, essentially. It's not like one gives a max and one gives a min. Not this time. Sometimes some Lagrange problems do give you a max and a min, but other times they may just give you a max, and other times they may just give you a min. And in this particular case, both of these points give a min only, minimum distance. Okay? So we have the critical points. Now, what is the actual minimum distance? Because I think they wanted that. They said minimize the distance. So you got to make sure that you follow directions, you know, and get everything here. So you're like, okay, well, remember the distance was the square root of the x minus 0, so square root of 5 halves squared plus the y minus 3 squared. So you put your y in there. And then figure out what this is going to be. I get square root of 5 halves plus, and this ends up being 1/2 squared. So this looks like square root of 5 halves plus 1/4, which is square root of 11/4, which is square root 11 over 2. And there's your minimum distance, okay? The exact answer. That's minimizing your distance. Now, how would you maximize the distance for this problem? I hope you could get that there is no answer for max distance, because look, the parabola goes on forever and ever and ever. And here's your point P. So, you know, the max distance would be infinity. So there is no max for this problem. I just want to point that out, because some people are sure there's always a max and a min for every Lagrange problem you do. No. This one's kind of interesting. Min only, and the max is infinite. Cool. You should be very excited that you can do these kind of problems now. This is like real deal. You know, you're putting calculus to work for you. Minimizing distance is kind of important. Okay. So what of it? So let's take a look at this problem. You're going to see this one in your MyLab math. So eyeballs up and open. And that's why I put it in the lecture, because I kept getting too many students. Once I put it in the homework, they kept coming to me and going, I don't get it. And it is hard. Okay. And the reason why it's hard is that there's a max and a min, but unlike the other max and mins we did where the max was the positive version and the min was the negative, the max and the min are completely different. And the other cool thing about this problem is, and what makes it hard, is that when you try and solve it for lambda, that approach that I've been kind of using every single time, it doesn't help you. You got to use a different approach, and you got to use that ZPP. ZPP, zero product property. If sometimes something equals 0, you can individually set the factors equal to 0. That property is going to save you many times. It's going to save us here. So watch how the ZPP comes and saves us. Okay, first up, let's get the Lagrangian. We're going to use Legrange multipliers. This right here is your constraint, and you always want to write your constraint where everything is on one side and 0 on the other, and that's easy because I'm just going to subtract 16. Okay. So now my Lagrangian, which is a function of 3 variables, because I just have a function of 2 variables for my fxy, and then minus my lambda, that's my Lagrange multiplier, and parentheses, I put my constraint in there. Beautiful. Okay, so we're going to extremize, that's not a real word, but Dr. Vallone used to use it. Extremize that function. Find that big function's critical points. Okay, let's go get the partials. Yay. What do we got? Okay, 8x minus, and then that looks like it's going to be 2 lambda x. Oh, my lambda is starting to look like an x. Not good. 2 lambda x. And of course, we'll set it equal to 0. Fine. We'll get the partial with respect to y. I got a 2y minus 6 lambda. I'm distributing this lambda over And then the last one, it looks like it's going to be 2 lambda y. Yep, equals 0. And then when I take the partial with respect to lambda, I'm just going to get the opposite of everything that's in the parentheses and set it equal to 0. And it's the same as my constraint. Fine. Now the fun begins. Okay. Here, if you try and solve for lambda with these two equations, you're going to run into a brick wall. You can go try it and find out what that brick wall feels like. I'm just telling you now, it's not going to work for you. So you're going to do a different approach. So the approach for us is going to be factor and use the ZPP. So let's do that for the first partial. So is there a common factor? Sure, 2x. And if I factor out a 2x, what's the other factor? 4 minus lambda. Okay, so now you use the ZPP. It says if something times something is equal to 0, individually set the factors equal to 0. Okay, now what do we have here? When I solve the first equation, I get x is 0. Or, this is always an or, not an and, or solving for lambda here, lambda is a 4. Okay, well, which is it? Well, we're going to get there. Hold on. This is where it gets a little dicey. So let's start with the lambda equals 4. Let's substitute it into the other partial and see what happens, just for fun. So if you notice that lambda appears twice in your partial with respect to y, so you're going to have to substitute it in there twice. Okay. So lambda is equal to 4 here, like this. 2y minus 6 times 4 minus 2 times 4 times y. So then what? Well, I get 2y minus 24 minus 8y. Okay. And then you can combine like terms. I get negative 6y, and then I'll add 24 to both sides at the same time, and then divide both sides by negative 6 and reduce, and I get y is negative 4. So what can I say? And this is what's dangerous. I'm going to put what not to do. The point 0, negative 4 is not a critical point. Why not? You just did all the work, and this is a danger zone because people go, look, I got x equals 0 up here, right? And now I got y equals negative 4, right? So I can just put them together, right? No, you can't put them together. Why not? Well, you can try, but it's not gonna work for you. Yeah. I mean, if you you'll see. It's just not. So what I'm going to cross that off. Remember that if your critical point, if you think you have a critical point in your hands, substitute it into your constraint here and see if it makes your constraint equation happy. Because if it doesn't satisfy your constraint, it's not a critical point. It's got to solve everything. So I encourage you to go plug this point back into that constraint where x is 0 and y is negative 4, and I don't think it's going to work. Okay. So now what? You're going to plug x equals 0 into your constraint. Because we did get that. We did get it. When? Well, up here, we're like, hey, x is 0. Okay. We'll plug that in the constraint. So remember, your constraint was x squared plus 6y plus y squared equals 16. And if you plug x equals 0 in here, then what? You get that. Oh my goodness. Well, this is a quadratic equation, so you better be very careful. I get students in this class, they can do calculus 3, but then you give them a quadratic equation and all hell breaks loose. They're like, what? I forget how to do that. Okay, remember a quadratic equation, the best bet is get everything on one side. So I'm going to subtract 16 from both sides and 0 on the other. You certainly could use the quadratic formula at this point because, you know, that'll work. But I think that's overkill because I think that this particular quadratic equation, we can factor and use the ZPP because this is factorable very nicely over the set of integers. Does anybody want to take a crack at factoring that lovely polynomial?
It's y minus 2 times y plus 8.
Mm-hmm. Great. Perfect. So factors. So yay, beautiful. So now we can go, all right, I'm going to apply the ZPP. So that means y minus 2 equals 0 or y plus 8 equals 0. And then I get two answers. Y is 2 or y is negative 8. So what does that mean? It means that when x is 0, I can have y be a 2 or y could be a negative 8. And folks, those are two critical points. But there's more. Oh, no, you're kidding. Reminds me of those Ginzu knife commercials. And if you're one of the first 10 callers, there's more. Right? You get the Bendix washer dryer. Nobody's laughing. So disheartening teaching on Zoom. Nobody laughs at any of my jokes. Okay, some people are saying LOL. I'm muted, but I'm chuckling. Thank you. Thank you for that. I'm chuckling all the time. You have to keep a sense of humor, people. I remember an old friend of mine many years ago told me that if you keep a sense of humor, that means you're spiritually evolved. See? Good to know. How do I get these other critical points? I claim there's two more. Are you kidding me? There's two more critical points? Where the heck are they? I feel like I'm done. No.
We still have y equals negative 4, right?
Good. You still have to deal with this thing right here. Putting stars by it. Yeah. What about that y equals negative 4? Does that come into play? Yeah. Now, we did agree that 0, negative 4 is not a critical point. But there's still going to be a critical point, or more than one, where y is equal to 4. So what are you going to do with y equals negative 4? You're going to plug it into the constraint, or substitute it into the constraint. See what happens. Okay, so you're going to go x squared plus 6 times y, but y is negative 4, plus y squared, negative 4 squared. That has to equal 16. And then get x. So we get x squared plus negative 24 plus 16 equals 16. Nice. Well, subtract 16 from both sides, and that kills off the 16s. And then add 24 to both sides. So you get x squared is 24. And then you know the drill. Take the square root of both sides. But what do you always have to remember when you square root both sides? Hey.
Plus or minus?
Plus or minus. Yay. Good. And then you get, okay, well, and you want to clean that up a little bit. I think 24 is 4 times 6. So you can simplify the radical a little bit. 2 squared is 6. So what am I saying? I'm saying I got 2 more critical points. Oh, man, you're kidding me. I got 4 altogether. This is turning out to be a major headache. Yeah, I know. It is. So you have 2 more critical points. Now, remember, when you're doing Lagrange, you don't have a d-test. You don't go off and find, any second partials or anything like that. It won't get you anywhere, okay? Good luck with that. Well, now what? Like, do I just say all of them are max or all of them are min? This is where the fun begins. You're going to plug all of the critical points individually, of course, into your original function. That's this guy way up here, your fxy. You're going to substitute into him separately, of course. And then whoever makes that function the biggest of all, that's going to be your max. And whichever point that you substitute in gives the smallest value, that's your min.
So it'd be okay if I write small notes, like saying like if lambda equals 4, y equals negative 4, or if y equals negative 4, x equals square root plus or minus square root of 24, and so on, right? That'd be all right to do, right?
I want you to do everything that I've done here.
Okay.
Yeah, I don't want you to go, if this is this, and then obviously this is this. I want to see the work. See all this work I had to do to show it? And if you magically go from one to the other, which I can't even do, you won't maximize your points. Because I want to see it. Don't skip steps. A lot of people miss a lot of points on their handwritten work when they upload for me, even though they have the right answer. I a lot of times take almost all their points away for lack of showing me the intermediate steps. While the right answer is nice, I want to see how you got there. I want to see the process and the thinking. It matters. So now what? So I claim by trial and error, and this is where I want to see all this trial and error. You're going to evaluate, the function at 0, -8, and then you're going to evaluate it at 0, 2, and then you're going to evaluate the function at 2 square root of 6, -4, and then you're going to evaluate at -2 square root of 6, -4, okay? And then show me all 4 of those. And it's going to turn out that the absolute min is this guy here. And I think the value was a 4. And he's like the smallest guy on the block, okay? And then the biggest turned out to be both of these guys. Both gave the same value. Both are maxes. And both of them gave, I believe, 112. So the final answer that MyLab Math wanted, that you would actually type in. You would type in the max and the min. And in this particular case, I don't think they wanted the critical points, but if that's missing on your handwritten work, I claim it will be kind of a problem. Okay. Okay, so I have a problem right now, business calculus problem. Use Legrange multipliers to maximize this function, fxy is equal to x plus 2xy plus 2y. And with this constraint, x plus 2y equals 80. Use the Lagrangian function I mentioned. Your answer, you need to give me a couple things. Give me the point or points that maximize the function, and then give me the actual maximum value that you get. And that's just simply plugging the point back into the original function. Okay, you guys think you can handle it? Thanks for telling me. So I'm going to recap this for the people that didn't get the recording. So you find your Lagrangian, which is this big L. So you have your function minus your lambda times your constraint. You find your partials. Lx is 1 plus 2y minus lambda equals 0. The partial with respect to y is 2x plus 2 minus 2 lambda equals 0. Your partial with respect to lambda is negative, and then the parentheses, which is basically the stuff we got from your constraint, equals 0. And that's your constraint. And now when you solve for lambda twice, so I'm going to take my Lx and solve it for lambda. I get 1 plus 2y. I love when that happens. Oh, my goodness. Lambda is equal to 1 plus 2y. And then if I solve for lambda for the other equation, I get lambda equals x plus 1. But lambda has to equal lambda. So I set the two lambdas equal to each other, and I get x is equal to 2y. Yay! Substitute that into your constraint. When you substitute x equals 2y into your constraint, you get 2y plus 2y is equal to 80. But that means 4y is equal to 80. But that means y is equal to 20. And then how do you get x? Well, x is supposed to be twice y, so x has to be 2 times 20. So, folks, there's your critical point. Now, you're almost done. You just need to evaluate your function at the critical point to actually get that maximum value, okay? And that's when you need a calculator. And you should get 1,680 if you did it correctly, okay? Thanks for letting me know about the recording. I appreciate if you always do that for the future. That'd be great. Bye for now.